Once the structure of the network is fixed, we need to train it. To do so, we have seen that we need to define a loss to be used inside the gradient-based optimization algorithm. We also need to specify a starting point for our descent algorithm, that is, an initial set of values for the weights and biases, i.e. the parameters of the network. Let us look into the weight bias initialization. Let us start with a very simple and maybe naive idea. We could initialize all weights and biases of the network with the same value. This is indeed very simple, since instead of choosing a very large number of initial values, we just need to pick one. However, such a choice happens to be disastrous. To do, see why, note that each neuron in the network would have the same weights and bias. In particular, each neuron of a given layer would perform the same operation, therefore producing the same output. So the network could be reduced to a network in which each hidden layer contains only one neuron. This was not our primary intention, since we usually want many neurons inside a layer in order to model different relations between the input of the previous layer. Initializing all weights and biases with the same value would lead to a network with a strong symmetry. All neurons behave in the exact same manner, which can also induce problems in the optimization procedure. And that this problem is even worse if the initial value you choose is 0, because if you use ReLU for all neurons, it implies that every neuron will output 0 and will be impossible to train. In short, do not initialize all weights and biases with the same value. For neural networks, a proper initialization is a random initialization. So how can we randomly initialize the weights? A first remark. In general, we have no prior insight to prefer positive or negative weights for a specific neuron. Indeed, since we usually do not have a clear interpretation of what each neuron is doing inside the network, we have no reason to add specific constraints, like positivity, on the weights and biases. Therefore, it makes sense to initialize the weights and biases with a distribution whose mean is 0 and which has a symmetry around 0. Two classic choices for the initial weights distribution are the normal distribution and the uniform distribution. Apart from specifying the mean, we also need to specify the variance for these two distributions. If the variance is too small, then the weights can be considered almost constant, equal to 0. The previous reasoning shows that each hidden layer can be reduced to a single neuron, which greatly damages the performance of the network. Besides, if ReLU are used as activation functions, each neuron is likely to output 0, making the whole network impossible to train. On the contrary, if the variance is too large, you may increase drastically the saturation phenomenon, which appears when the linear combination of the input is very large, positive or negative. This can happen if the inputs are not normalized, but also if the weights take very large values. More generally, if you notice that the weights are very large at some point during the training, you may want to add a penalization term to prevent the weights from exploding and consequently limiting the saturation phenomenon. All in all, you have to find a trade-off between initializing the weights with small values that would damage the approximation power of the neural network and choosing large values that would increase the saturation phenomenon, making the convergence of the optimization procedure slower. Contrary to the weights, the biases of a network are chosen deterministically. They are often set to 0. You can also initialize them with a positive value if you use ReLU activation function to encourage the neurons to activate. Now that we have said that the initialization of the weights must not be too large or too small, we make this statement more precise. I present here one of the two most famous initializations. The main idea behind the first initialization method is that the variance of the output of a neuron in a given layer should be of the same order as the variance of the output of any neuron in the previous layer. Indeed, you know that the saturation phenomenon appears for large values of the linear combinations used as the input of a neuron. To limit the saturation, you would prefer the variance of any linear combination to be of the same order throughout the network. This is a general principle on which this initialization is based. Beware, here you enforce the variance of the linear combination to be of the same order throughout the network only at the initialization. It may happen that these variances change during the training of the network. Preserving these variances during the training would require putting additional constraints on the weight during the training as a penalization term in the loss, which is not the subject of this slide. Here is the other most famous initialization. There are two differences between this initialization and the previous one. First, the distribution is either normal or uniform. This is not a major difference, since the analysis relies on the variance of the distribution, no matter what the precise distribution is. The main difference is that this initialization but constrained not only to enforce the variance of the linear combination to be of the same order, but also to prevent the saturation phenomenon directly in the backpropagation step. Indeed, you impose constraints so that the expectations of the partial derivative of the loss are of the same order through the network. Roughly speaking, it means that the expectation of the gradient is forced to stay constant through the network. This later constraint, together with the first constraint enforcing the linear combinations to be of the same order, leads to this initialization, in which the variance, the denominators, depends on both the numbers of neurons of the current layer and the next one. You can look at this paper if you want to know more about initializations and its impact on the training and predictive performances of neural networks.